Okay, so last time we worked a method, we used the Ritz method, we worked a problem. Um, and then we talked about, those problems we worked, I kind of came up with the polynomial interpolance in a not very systematic way, and now we've introduced a systematic way to come up with interpolance. So now we can introduce the finite element method, right? So starting with what I'm going to do right now, we are going to be doing the finite element method. So let's return to our model problem. I'll just write it down. We've used it before, but I'll write it down again. We're going to solve this on the range, or look at this on the range A to B, subject to Neumann boundary conditions. What's another name for Neumann boundary conditions? Natural boundary conditions, right? So I'll write down the weak form. We know how to do that. We're going to multiply by a test function, integrate over the body, integrate by parts, and apply the boundary conditions. So if we identify the terms in our bilinear form, that b of del u is the first integral. And the L del U term is that thing. And now we're going to solve the problem, the variational problem that looks like this. So before we inferred, even though I mentioned it's the same, ultimately it's the same problem, but before we inferred a quadratic functional from that, now we're just going to use it directly and solve it. And so what we're going to do is we're going to let u be approximated by u of h, which is equal to sum over j equals 1 to the number of shape functions nj uj, where nj is of degree n minus 1, and the uj are the unknowns. And I mentioned, and so we're going to solve this problem. So I mentioned when we talked about weighted residual methods, there were different types of weighted residual methods. So I mentioned the Galerkin method, the Petrov-Galerkin method, the least squares method, and then we talked about the Ritz method. Well, we're going to solve this ultimately by the Galerkin method, and the way I define that is that for our test function, we're going to use the same interpolating functions that we use in our approximate solution. Okay, so then ultimately this will be B of Ni, Nj, Uj equals L Ni. Okay, and we'll see what that looks like in just a second.